So yesterday we started talking about conditional probability. We are going to continue that today. Our focus today will be using a tree diagram to help us lay out how to find the probability as opposed to using a table like we did yesterday. All right, so this was the formula we had yesterday. Okay, and remember I said there was an alternate version of that. Okay, I'm fine with you using either one. But it's good to know that both of them are out there, right? We can manipulate one into the other depending on the kind of information that we're given. So we're going to use that formula along with a tree diagram to figure out the probability when we have dependent events. So the first question here says, a school system compiled the following information from a survey it sent to people who were juniors 10 years earlier. 85% of the students have graduated from high school. Of the students who graduated from high school, 90% are happy with their present jobs. Of the students who did not graduate from high school, 60% are happy with their present jobs. So remember yesterday I said sometimes we're not given all of the information to completely fill out a table. All right. So instead of giving us specific numbers of who they talk to, how many people they talk to, they're just giving us an overall percent. All right, but we can set it up with a tree diagram. The question we're being asked is, what is the probability that a person from that junior class 10 years ago graduated from high school and is now happy with his or her present job? Okay, so we are going to break this up into events A and B. So what is the first thing, the first event that we're talking about? Did they graduate or not? Okay, that's the first situation. What's the second one? Are they happy with their job or not? Okay, so we are going to do a tree and branch off. Did they graduate or didn't graduate? Okay, that's the first thing that we have to decide. Once we know which path they are on, each of those breaks out into being happy with their job or not happy. Okay, so this first one is event A, and the second one would be event B. Does that make sense? Are these dependent events? Is being happy with your job dependent on whether you graduated or not? If it's not, we should have the same probability regardless of whether we graduated or not. Do we have the same probabilities of being happy? Yeah. Do we? 90% are happy, the ones who graduated, only 60% if they didn't graduate. Does that make sense? So there's something about graduating or not graduating that is affecting what kind of position, what kind of future job they're getting, and if they like it or not. Does that make sense? Okay. So what we want to do is we want to put these probabilities that were given on the branches. Okay? And the rule that you have to follow is anytime something branches out, those branches have to add up to 100%. Okay? So when I branch to graduating and not graduating, I have to account for 100% of the kids, right? They graduated or they didn't. Those are the only two options. Okay? So what did it tell us about the percent that graduated from high school? 85%? Okay, so I'm going to put 0.85 on that branch. What would the other branch have? 0.15. Yep. So we want those to always add up to a 1 or 100%. Does that make sense? Okay. The next statement says, of the students who graduated. That's like the given statement that we had yesterday, right? Knowing that they've graduated, 90% are happy. So we have to branch off of the graduating part. All right, we already know they were here, and now we want to go out to them being happy. Does that make sense? So this branch would be 90%, or 0.9. So if of the students who graduated, 90% are happy, how many are not? 10%. Okay? Next statement says, of the students who did not graduate, so again, given that they didn't graduate, 60% are happy with their present jobs. That would be this branch. Okay? So, what percent would not be happy? Okay. Questions on how we create the tree diagram? Okay. The question now says, what is the probability that a person from that junior class 10 years ago graduated and is happy? In order for both of those situations to be true, we have to have gone on this branch to graduate, and we have to go on this branch to being happy with the job. Does that make sense? Okay. If we were to set it up using the formula we had yesterday, we would write it, the probability that they graduated and are happy equals the probability they graduated times the probability that they are happy given they've graduated, right? That's the one we had yesterday. So what is the probability they graduated from our tree? That's the 85%, right? That first branch. What would be this piece? They're happy knowing that they've already graduated. That's this one. Yes? And the formula is telling me we multiply those together. So in a tree diagram, to get out to here, so they've graduated and they're happy, to go out that complete branch, we just have to multiply the probabilities of our path. Does that make sense? So to be graduating and happy, we're going to multiply the 0.85 and the 0.90. So 85% and 90%. Because 90% of these kids are happy. Does that make sense? So what do we get if we take 0.85 times 0.90? All right. Okay. What is the probability that a student from that same junior class did not graduate and is happy? What would we do? Did not graduate and is happy. So again, probability didn't graduate and is happy would be the probability that they, what's the first event? Didn't graduate times the probability that they are happy given that they didn't graduate. Okay? So your second branches, all right, in this section, these are the conditional ones, right? Because we already have gone out one branch. We already know if they graduated or they didn't graduate. That's the given piece, right? Then we're getting out to the second event happening. Does that make sense? So we want to go which route? We want to go didn't graduate and is still happy with their job. Yes? So we're going to multiply the 0.15 and the 0.6. All right. What do we end up with? Okay. All right. Our next example says use the following information to create a tree diagram. Then calculate the probabilities below. It says 45% of the senior class is male, Of the male students, 60% have a part-time job. Of the female students, 35% have a part-time job. So I want you to talk at your tables. What do we have for events A and events B? What are these boxes going to get filled in with? All right, let's just double check that we have our events correct. What did you do for the first branching? Okay, male and female. And then what's the second event? They have a job or they don't, yes? Okay, so job and no job? All right. Continue on, plug in your percentages, and then figure out what path they're asking you to take. Okay, filling in our percentages. What percent is male? 45%. So female would be 55%. Okay? Then it said, of the male students, so given that they are male, meaning we are already out to here, 60% have that job, right? Which means 40% don't. Okay? Given that they're female, so we're already out to here, 35% have a job, which means 65% don't. We okay with the numbers? All right. The first question says, what is the probability they are male and have a job? To get to being male and having a job, we have to go out this branch and this branch, correct? Okay. I'm going to keep writing it as that formula, okay, so that we can refresh our memory with that. So this would be the probability that they are male times the probability they have a job given they are male. Yes? So the probability that they're male is the 0.45. The probability that they have a job given that they're male is this 60%. And when we multiply those together, we end up with, what was it, 27%? Okay. The second one says, what is the probability they have a job? Which branch can you take to get that answer? Both. There's two different branches, right? All they're saying is we need to have a job. So we want to get out to here or out to here. Doesn't matter if they're male or female. Now, if it's an or situation, I can take that top branch or I can take the bottom branch. What do we do with our numbers? We're going to be adding those two things together, right? So to get out the top branch, we had, what was it, 45%? And then 60? To get out the lower branch, we have 55% and 35%. Yes? So we're going to have to figure out both of those quantities and then add them together. Go ahead and do that. We do already have one. Yes. All right. What do we end up with for a total? All right. Does that make sense? Yes? So this first one was male and job. The second part was female and job. All right. And it didn't matter which one we had. Okay. Part C is asking for the probability that the person is male given that they have a job. Correct? So we're kind of working backwards. I want you to write it out based on the formula that we've had. Remember, it's always probability of B given that A has already occurred. In other words, given that we already know they have a job, what is the probability they are male? Okay? So, job is event A. So this would be the probability they have a job times what? Probability they have a job times, sorry, I should rewrite this here. Probability that they have a job and are male is the probability they have a job times the probability they are male given they have a job. This is what they're asking me to find. Right? If we base it off of that formula, the probability of A and B is the probability of A times the probability of B given A. Right? So this is the piece that's the unknown. What is the probability they have a job? We just calculated it. What's the probability they have a job? 46.3%. Yes? Okay, as a decimal, we'll just do 0.46. Was it 3 or 2.5? Okay, we'll go back to that. Okay, so, what is the probability they have a job and are male? Did we already calculate that one? That was part A? So 27%? So can we work backwards and figure out the missing one? What would we have to do? Divide. So we're going to take that 27% and divide by the 46.25%. What do we end up with? What was it? 58.4? Okay. So for events A and B, we're talking about getting all the way out to the end of the branch. Yes? This first piece is the probability of A. The second chunk here, these are the probabilities of B given A. And if we go all the way out to the outside, we get the combined probability of A and B. Does that make sense? Okay. You need me to scroll down? All right. I'm going to give you guys a couple minutes. I want you to try this. It says use the table at the right to find each of the probabilities. Go ahead and do both questions. All right, so while you were working, I put totals for each row and column up there. Are we agreeing that those are correct? You had a total of 1,200? Okay. So the first question says, what is the probability they have less than a high school education? So less than high school education, we could use all of these, correct? So what's our total? 107 out of the 1,200, which comes out to be about 9%? Okay. Second one, probability they earn over 30,000 and have less than a high school education. Now we're being very specific. We want them to be over 30,000 and have less than a high school education. We're looking for where those two quantities meet. Okay, which would be 2 out of 2 out of the 1,200. Yes? Okay. And that ends up being about 0.2%? Okay. The third one earns over 30,000 given that they have a high school education. If it's given, what do we have to do? We have to start there, right? We have to restrict our table to just that information. So, given that they have only a high school education, we are only going to look at this piece, correct? So what is the probability they earn over 30,000? Now we're looking at just the 14 out of 224, correct? And that you should have had about 6.25%. So remember, if there's a given, we're looking for a conditional probability, we're only using one row or column from our table. Okay? The last one says, what is the probability they have a high school education or less, given that they earn over $30,000? Now we're looking at what? Which part of the table am I limited to? The over 30,000, right? The given piece. I'm limited to just this information. And the question says, what is the probability they have a high school education or less? That means we could use either of these. So we have a total of 16 out of 404. Which gives you about 4%. Okay? Remember how to use the tables? Okay. Last question. It says the senior class is 55% female, and 32% of the class are both female and they play a competitive sport. Okay? We are told the probability that the person is female is 55%. The probability that they are female and they play a competitive sport is 32%. Yes? What is the probability that a student plays a competitive sport given that the student is female? So in this situation, what is A and what is B? We want to play a competitive sport given they're female. What has to happen first? We have to know they're female. So this is event A, this is event B, correct? Going based on that formula we had, the probability of A and B is the probability of A times what? Probability of B given A. Yes? All right, so plugging in what we know. Probability that they are female, that was event A. All right, probability they were female was 55%. The conditional piece is what they're asking us to find. So that's our unknown. And what do we know about the and? They're female and they play a competitive sport. 32%. How are we going to find it? What do we have to do? Divide. All right, so take 0.32 divided by 0.55. And we end up with, what do we get? About 58%? Okay. Did we need a tree diagram on that one? No, you may have started to draw one, all right, which is fine, but they were only asking us about the female branch of that tree, so we really didn't need the other option. Okay? All right, so there is your day 2 assignment. Notice it's on a couple different pages.